Alrighty, my presentation will be on TimSort, an algorithm created by Tim Peters in 2002. So as previously mentioned, uh, TimSort was created by Tim Peters. He was a day-to-day software engineer. He wasn't in research. He wasn't in graduate school. He just made an observation about real-world data, the data he was working with, and he sought to exploit the tendency that he noticed about the real-world data. And the algorithm really is quite fascinating. It's used as Python's standard sort function and has been since the algorithm's creation in 2002. It's also been used in Java, I believe, as their standard sort function. Um, One more fun fact, Mr. Peters is actually the writer or the creator of the Zen of Python, which is a neat little poem guideline for writing good Python code in Tim's opinion. TimSort has three general stages. We're going to define our runs, perform insertion sort on these runs, and finally, we're going to merge these runs into our final sorted array. At this point, we're done. We're also going to talk about a merge modification towards the end, but TimSort is much more than just a hybrid of insertion sort and merge sort, and we'll see why shortly. First stage of TimSort is defining our runs. So a run is just a sequence of data, and a natural run is a sequence of sorted data that naturally occurs in our input array. And this tendency for naturally occurring sequences of sorted data within our input arrays is the tendency that TimSort seeks to take advantage of. Now, we also need to set a min run size. So this is going to be the size of the runs that we create, the minimum size of the runs that we create. We're going to set this number between 32 and 64 inclusive. And the reason for this is to not only keep our runs small so that insertion sort can perform optimally on them, but also not too large, or rather not too small to the point that we have to have so many runs and then therefore perform so many merge operations. As another note, we'd like the number of runs we have to be equal to 2 to the power of something. This also improves merge functionality. But anyways, as we're traversing our array, we're defining runs. If we happen to come across a natural run, a sequence of already sorted data, we're going to define that as a run. And we're going to, if need be, add elements, unsorted elements, to that run, that naturally occurring run, to reach our min run size. And once we add those elements, then we have our complete run. So maybe you picked up on it. There are three possibilities for our runs. We could have a very large naturally sorted run, much greater than the min run size. We could have a hybrid of a natural run and unsorted data added to it to reach our min run size. Or we could have a run of unsorted data. Again, would be the min run size. Once we define our runs, we pass them to insertion sort. So depicted below is a comparison between insertion sort on the left and quicksort on the right. Of course, I'm stating that insertion sort runs faster or in less time than quicksort, which is should come as a surprise, a bit of a surprise for us students, being that we know that n log of n is a better runtime than n squared. But due to the constant factor of insertion sort and the constant factor of quicksort, for a small enough n, we'll actually find that insertion sort runs faster than quicksort, again, due to the constant factor. Furthermore, when we pass already sorted data, the runs that we find, the natural runs that we find, or mixtures of sorted data and unsorted data, insertion sort performs in O of n time, or rather omega of n time. So it's going to be optimal both in the case when it's completely unsorted, and even more optimized when we pass sorted data to it. After our runs are sorted with insertion sort, we pass them along to a merge functionality. So similar to the merge functionality in merge sort, we're going to be merging subarrays into our final sorted array. And this will complete our TimSort algorithm. But to do so, we're going to use a pseudo stack. I'm calling it a pseudo stack because we're actually accessing the top 3 elements of our stack compared to a normal stack. We only access the top element. In this pseudo stack, we're storing references to our runs, but essentially we're just storing the runs. What we're doing is we're maintaining balanced merges, and balanced merges optimize the merge functionality. We're also maintaining stability, which is of course very important with real-world data, or can be. To do so, we're adding our runs from left to right as we go, and we're checking this condition, these 2 conditions. As you can see in this example below, the length of x plus the length of y is less than the length of z, and therefore we're going to merge x and y. This again allows us to do more balanced or semi-balanced merges. So that sums up the process of TimSort: defining the runs, passing them to insertion sort to be sorted, and then merging those runs. But there's another optimization we can do, particularly or specifically in the merge function. So just looking at our basic merge operation, if we have 2 arrays, array A and array B, we're going to be comparing the first element of array A to the first element of array B. The smaller of the 2 elements, 2 in this case, will be passed along to our final array. We then continue this process, iterating through array A. Now you may notice that a chunk of this data, 2, 3, and 4, all happen to be less than our value 5 in array B. And because we're dealing with sorted data that's already been passed to insertion sort, all the data in array B to the right of our value 5 here is going to be larger than 5, and therefore anything in array A that's less than 5 is also going to be less than all the other data in array B. So the optimization trick we're going to do is called galloping, and it attempts to take a big chunk of data rather than just 1 bit at a time and move it all at once, effectively reducing the number of comparisons we have. So to do galloping, after a certain number of iterations in which all the elements from array A are less than the elements in array B, we're going to perform binary search on that array. And remember, this array is sorted, so binary search is a valid search method. And what we're going to be searching for is the first element that's greater than 5, the first element in array B. Once we find that element, we take the entire chunk to the left of it, the entire chunk that's smaller than it, and we pass that along to our final array. So it greatly reduces the number of comparisons that we potentially have to do. Looking at the complexity of this algorithm, we of course see that TimSort is a top-tier algorithm. It is, as mentioned, used as Python's standard sort function and has been used in a variety of other languages as well. So the worst case runtime, of course, lines up with merge sort and heap sort. Average case, which largely has to do with the assumption that there is going to be somewhat sorted data in our array already. So we're going to have to perform about n comparisons for our insertion sort and log of n merges. And the best case, when the data is already sorted, it's just a simple insertion sort which, as we can see, the best case for insertion sort is omega of n, so TimSort follows as well. Now, a note on the worst case scenario, it actually wasn't formally proved until a little more recently, and it's not something that I'm going to go into in depth, but I do want to point out that for the case of completely descending data, we would just classify that as one big descending run, and in the sake of optimization, we're going to perform a blind reverse on that data. So in terms of comparisons, that's only n comparisons and then n over 2 swaps. So in no way is it worse than n log of n even. The worst case would be something more like a bunch of unsorted data that doesn't have large runs, doesn't have a lot of runs, not just the completely descending case. Here's a nice depiction of TimSort in action. We can see on the y-axis we have the position of a particular element. On the x-axis we have time. So we can see insertion sort occurring and then the merging process as well. I thought it was a neat image. So that concludes our TimSort algorithm. To recap, we define our runs based around the belief that there's going to be naturally occurring sequences of ordered data, natural runs, in our input data. We then pass those runs to insertion sort, which performs optimally on those small or partially sorted sets of data, and then we merge those data, those arrays, those runs, and we use galloping to merge them in chunks rather than one by one. And that completes the algorithm. I do want to point out though, if you want to check out the visualization, the guy makes visualizations for a bunch of other algorithms, and that would be this corte.si. And for some general good information on the algorithm, infopulse.com, this blog that was created about TimSort, is a great blog as well.